Alrighty, so now we're going to see if I can figure out how to do a remote presentation. The next talk will be given by Daniel Castro-Cisneros, who is on Zoom, and hopefully you can unmute and share your screen.
Hi everyone, can you all hear me?
Yes, and I will turn the volume up here in the room and mute us. Although we see you, I'll stay off mute until we see your screen.
Okay, can you see my presentation over there?
Yes, thank you. All right. I'm going to mute the room.
Okay, good morning everyone. Thank you for having me here. I will be presenting this investigation on the dynamics of lunar impact ejecta that I have done with the guidance of my advisors, Renu Malhotra from University of Arizona and Aaron Rosengren from UC San Diego. So impact events on the moon can generate a high velocity ejecta, which is capable of escaping from the lunar gravitational field, and they can either reach the Earth or they could also escape into heliocentric orbits. So some important early studies were done in the mid-90s, mainly by Gladman, who showed again that these lunar ejecta may hit the Earth within a few tens of thousands of years, and they could also reach heliocentric orbits. Some more similar studies were made by Alvarellos and collaborators for the Saturnian satellites. However, some more recent advances in numerical integrators, computer power, and the discovery of some interesting NEOs motivate some new higher resolution studies on this matter. Particularly, we have the discovery of a couple of NEOs, which may be of lunar origin. These are Camoleva and the Minimoon 2024 PT5. These two have been spectrally linked to lunar samples. This was done by Sharkey in 2021 and Carreta in 2024, respectively. Our own simulations have shown that there is some evidence for this possible lunar origin of Camoleva. We have shown that its orbital dynamics is compatible with this origin. Additionally, Zhao has pointed out that Giordano Bruno could be a possible source for these objects, and its creation event could have created hundreds of escaping fragments, which are at least as big as Camoleva, in the order of around 50 meters. So with all of this, we have done some new numerical simulations. For this, we have selected 3 lunar latitudes at the North Hemisphere, Equator, South Hemisphere. From each latitude, we are selecting 4 launching sites at the near, leading, far, and trailing hemisphere. And from each of these, we are launching 500 test particles in a cone center at the local vertical at each of these launch sites. Now, the launch speeds range from the lunar escape speed of around 2.38 kilometers per second up to 6 kilometers per second. These test particles in these simulations were evolved for hundreds of thousands of years using the IS-15 integrator in the Rebound software package. This includes the gravitational interactions with the Moon and with the 8 planets of the solar system. Now, a difference with previous studies on this is that previous studies have mostly relied on uniform distributions for these speeds. And in this case, we're using speeds derived from the power law derived by Zhao for this kind of large impacts would create a crater similar to Giordano Bruno. So again, this would generate hundreds of fragments of tens of meters of size with this velocity distribution. So peaking around between 2.5 and 3 kilometers per second. Here's a first summary of the results that we have found. These are the possible fates of lunar ejecta. So in this 100,000 of years time span, around 23% of these have collided with the Earth. Only 1% returns and collides back with the Moon. Around 63% remain in the near-Earth heliocentric space. 11% migrated into the near-Venus heliocentric space. And among the 6% that remains in the near Earth space, a fraction of this is able to go into a co-orbital state. And an even smaller fraction can reach a quasi-satellite state, which is the current state of objects like Camel Leva. So over here, we also notice that most of these objects, they belong into the either the Athene or the Apollo asteroid families. And again, we have this very narrow region, which corresponds to the co-orbital region. And again, a small fraction of these escaping fragments were shown to occupy this region. Okay, so here is a summary of the colliding particles. So this is divided by each of the launching sites. What we have found mainly is that the collision rates between the three launch latitudes at the north, equator, and south hemispheres are very similar. The main conclusion that we have from here is that the trailing site is consistently the site with the largest production of colliders with the Earth. And this is in accordance with some previous studies that also showed that most of the colliders came from the trailing hemisphere of the Moon. We can also look at the temporal distribution of these colliders. So mostly, most of the collisions occur within the first 10,000 of years, but actually around 10% of them occur very early in the first 10 years. We also observed that the cumulative number of collision follows a power law distribution after 10,000 of years, following, again, the cumulative number of collisions is proportional to the time up to this exponent. So this shows a somewhat slowly falling flux in these time scales. We also looked at the speeds at the moment of entry at the atmosphere. Over here, we defined the collision with the Earth at a 100 kilometers altitude. So we can see that the speeds are quite low, so ranging from 11 to 13.1 kilometers per second. For comparison, an object like the one from the Chelyabinsk event in 2013 had a speed at entrance of around 19 kilometers per second. So this is both very low speeds and also very narrow range. Another thing that we found is that the colliders with the largest entry speeds are delayed colliders. So these are the ones that collide with the Earth after this initial 10,000 of years. So this is most likely due to close encounters with the Earth before the moment of impact. We also looked at the latitude distribution of these collisions. Here we are mapping the ecliptic latitude at the moment of impact. And we see that a large fraction of these impacts occur near the equatorial latitudes, which is not very surprising. But this distribution is more concentrated at the equator than a uniform distribution, which is here shown in black. So we have calculated the ratio of the flex per unit area at the equatorial bands and at the polar bands. And we have found a ratio of around 0.76, showing again that these collisions are more heavily concentrated at the equator. In contrast, previous studies on air colliders from the general NEO population found a ratio of 0.9. So this is showing that these lunar originated colliders are more concentrated at the equator than the general NEO colliders. We can also look at the local time at the moment of entrance. And what we observed is that the AM and PM impacts are nearly balanced. This is nearly symmetrically distributed. Uh, so previous studies on the distribution of impacts from the general neo population showed that there can be large asymmetries in the AM-PM distributions depending on the speed ranges. This is not the case here because again we have a very narrow speed range. We can also observe a couple of peaks in this distribution at 6 a.m. and 6 p.m. This diurnal peak could be explained with the leaning hemisphere of the Earth just facing the particle flux. While this nocturnal peak would correspond to particles reaching the Earth from its trailing side due to them having very Earth-like orbits. And this will again be related to the fact that these reach the Earth with very low relative speeds. So here's a comparison between the air colliders with lunar origin versus the ones from the general NEO population. So again, lunar ejecta enters at lower speeds in the order of slightly larger than 100, than 11 kilometers per second, while the average speed of the NEO colliders is around 23 kilometers per second. Lunar ejecta impacts are more concentrated near the equatorial latitudes. The AM/PM distribution is nearly symmetrical, while for the general NEO population, there can be an excess either in the PM or AM range, depending on the range of the speeds. Lunar ejecta would represent a small fraction of the total impacts of similar size NEOs. We estimate at around 3%. We also were interested in finding the possible contribution to the near Earth space of these particles, not colliding, but just staying near Earth. So we have found that the particles within a few hill radius from the Earth, they decrease very rapidly, but they can reach a small asymptotic value, which is on the order of a few particles. So a few particles in average populate the near space according to these simulations. So here are some conclusions. Again, we have found that a large fraction of the escaping lunar ejecta collide with the Earth in timescales of around 0.1 megayears. This flux is decreased by half over only 10,000 of years. The trailing side is ejecta from the trailing side are nearly twice as likely to reach the Earth as those from the leading side. Again, Earth impact locations of lunar ejecta are more clustered around the equator, and they are roughly equally distributed in the AM/PM ranges. For following up studies, we would like to consider the case of oblique impacts at the moon. The distribution of velocities that we have used is for a large vertical impact, so oblique impacts should be reassessed for a next study. We would also like to study the dynamics of lunar ejecta at some ancient times, so with a different lunar orbit, which would correspond to the heavy bombardment era. We would also like to investigate long-term evolution in the heliocentric space and higher resolution evolution of the lunar ejecta in the cislunar space. And this would be particularly important in the event of something like 2024 YR4 actually colliding with the Earth in the following years. You can check out more details in the paper that we published last April on this. I will be defending my PhD dissertation next week at the University of Arizona. So I'm still looking for job opportunities. If you would like to connect, I would be very happy to talk with you about any openings. Thank you. I will take any questions.
All right, thank you, Daniel. And apparently there are lots of clap emojis. I'm going to say we have time for a very quick question or two because there are two hands raised. I'll go with Bill first.
Okay, can they hear me with this way?
Should,
Okay.
yes.
Thanks for the talk. I just have a quick question. Of the objects that become quasi-satellites, how long do they stay in that orbit?
Okay, yes. So we have another couple of papers on that. How long do they stay? Most of them, they stay for the order of 100 years. But we have found rare cases in which they can stay in either a quasi-satellite or more likely in a quasi-satellite transitioning to horseshoe states for hundreds or tens of thousands of years. But those are rare cases. In most of the cases, they stay in orbital states for the order of decades or a couple of hundreds of years.
Okay. Kelsey?
I'll do mine in the chat.
Okay. All right. So Daniel, please look for the chat in about 30 seconds to a minute or so for Kelsey's question. And let's thank our speaker again real quick.